Hello, my name is Mr. Bone. I'm the head of physics here at Ralph Allen School, and I'm here to talk to you a little bit about the physics course that we offer, why you may want to study it, what it entails, and where you can go with it after sixth form. I do love this Einstein quote. It unifies every single physicist I've ever met. Passionately curious. If you're somebody who looks at the world and goes, hang on, why does that work that way? That's interesting. And sticks to the problem, that is a really, really strong skill for this course. Now, there are loads of reasons why you may want to study physics. I mean, you're watching this video, so I assume you are interested. It may be because you love the way that the universe follows a few set rules and you can predict anything that happens and it makes sense. It may also be that you are interested in this because you know when it stops making sense. How when we look at things like quantum physics, the physics that we have breaks down and stops working. So loads of really exciting reasons, which would all be a very, very good reason to study physics. There's loads of good careers available through physics, and it is a great springboard to help you into any subject at university that you may want to study. So I'd massively recommend it. That's me. Let's have a look at some of the cool stuff that physics does. So looking at the frontiers of physics, I'd like you to imagine that you're looking at a spot of space in the sky taking up only that much size, as if it was a tennis ball 100 meters up in the air. Tiny fraction of the sky around you. NASA took the Hubble Space Telescope and pointed it at that section of sky, or at least that angle of sky, at an area which was previously thought to be black with no stars. And this is what they found. After opening the shutters of the telescope for 10 days and taking in all of this light, they saw these galaxies. Tremendously bright night sky, with light coming in from galaxies which took 12 million years to travel to us because they're so distant. What this means then is that we're looking at some of these galaxies 12 million years ago. These galaxies are probably dead or very, very different now compared to what they were like when the stars reached us. Very, very strange. And then Hubble decided to go one step further. They looked at a dark spot within this and noticed that they got even more stars from there. They were able to identify that there was a range of different galaxies, and they were looking back even further in time, and then repeated it again in, I think it was 2012. We've now got another telescope which is heading up at the end of this year and the start of next, the James Webb Telescope, far more powerful than Hubble, and it will give us a lot of information about the universe in which we live, which is great. Very exciting time. It's an exciting time as well if we look at the small things. So CERN over in Geneva are smashing together particles at very, very high speeds and looking at what comes off them to try and explain what our universe is made up of at the very smallest scale, using international collaboration from people across the world. Huge stuff. But of course, physics isn't just looking at the very big and the very small. Everyday engineering, such as everything in this photo, involves physics. The glass you need to make the shard, the structure of Tower Bridge in order to cope with the forces of the cars moving across it, the buoyancy of the ferry on the river, the circuitry required for the electric lighting. Everything in this image has been designed using physics. Huge. So as a result, there's loads of careers that you can go into, not just related directly to physics, but linked in alongside. Looking at the bottom of this screen, philosopher, something which you might not expect, but I did physics and philosophy at uni, fantastic crossover, looking at the paradoxes of quantum mechanics and time travel paradoxes. One of my friends who I did physics with at university is now working in law and patenting. So he looks at patents and analyzes whether or not they work and whether they can be allowed. using his physics background. Safe energy and reliable communications are huge things. Basically, you can go into doing anything. It's fantastic. In terms of the school, before that, the courses that you may want to do, a lot of them require physics as an absolute essential, and many of them want it as a desirable. So, for example, physics and engineering have physics A-level as essential things. Geology really benefits from having physics, but isn't an essential, for example. At Ralph Allen, we've got a very successful physics department with lots of student interest and uptake. Last year, we had 100% of our grades being from A star to C, which is phenomenal. And 73% of our grades were either A star or A. It's challenging as a course. This is one of the reasons why physicists are so sought after. We do require you to have a grasp of science, maths, and English. So we do require you to have a 6 in physics and another science if you're doing separate sciences, or a 6-6 in combined science. But because of the mathematical demand, we require you to have a 6 in maths. And because of the extra explanations that you need to provide and the clarity from that, we need you to have a 5 in English. If there are any issues with that, come and have a chat with us, let us know. But we're very well catered for at Ralph Allen. We've got a lot of very passionate teachers, 4, now 5 qualified physics teachers, if we include Mr. Greenoff as well, where our A-level classes are taught by 2 physics teachers each who specialise in their side of the course. So you're being taught by experts. On these modules then, the course is structured so that you start off with both teachers teaching you the very basics of physics and how we work with it, giving you the tool set you need. And then we branch off into our 2 different sides, which don't exactly map out this way, but you go through learning about forces and motion, electrons, waves, and photons. All of these, by the way, I'll go on with the next slide. And then looking at the very, very large and applying what you've learned. It's assessed with 3 exams at the end of year 13 in the summer. That's what dictates your grade. But there's also what's called the practical endorsement, where we can give you your grade as well as saying, yep, you've passed the practical endorsement. In other words, going on to this, there'll be loads of practical activities across the course. And if you can demonstrate a certain level of practical skill throughout those, we can say, yep, you've passed that practical endorsement as well to go with your degree, sorry, to go with your A-level grade, or you didn't quite pass it. We've been very successful at the school with people passing it, which is good. So going through these topics, Module 2, looking at the foundations of physics, is the toolkit that you need, looking at vectors, scalars, units, quantities, and working with standard form, giving you the mathematical stuff you need. Moving on from that, in Module 3, a lot of this will seem familiar from GCSE, apart from materials, which is a little bit new for you. All of this stuff builds on what you've got from GCSE, but teaches it anew, and goes through a lot more complex examples, stuff which you can really get your teeth into. So, for example, linear motion, we're looking at projectiles, things which are fired, but are accelerated downwards, but not accelerated along, so they follow a parabolic path. I taught a pirate-themed lesson on projectiles this year, which was great fun. And if we look at the next topic, again, a lot of this will seem familiar from electricity, but we go into it in more depth and more complexity. Waves, we really get our teeth into the mathematical treatment of it. We look at waves in musical instruments. We look at waves in communications and what happens if we put waves through 2 slits. The pattern that we get on the screen is really confusing, needs a different model of understanding. And we look at the mathematical treatment of that as well. Quantum physics, whoa, this is great. This is where the universe stops behaving. where light is both a particle and a wave at different points in time, and you need to use different physics to look at it. And if you look at it too closely, it stops behaving, and you can't do the physics. It's brilliant and infuriating and very, very cool, which usually causes a few headaches. Good place to start learning. In year 13, we take this skill set that you've developed over year 12, and we apply it to interesting stuff like fields in gravity, to stars, to looking at the origin and the nature and the end of the universe, to looking at how gases behave in thermal physics. Huge stuff where you really become into your own as a student of physics, knowing about how the world works. And then finally, we've got some rather interesting applications. Other kinds of fields like electric and magnetic fields, charging things up with capacitors, and then looking at particles in terms of their radioactivity, nuclear physics, and what the universe is made of. We've also got a rather interesting section on medical physics, using physics to investigate the human body and medicine, such as just behind you, where we've got an X-ray of Mr. Forrester's knee when he busted it. So we'll be looking a lot into that. It's a very exciting time. Lots of changes are happening in physics in the world at the moment, and I'm really looking forward to having conversations with you if you are interested in doing this course. Direct any questions to me. You've got my email just down there. I'd be more than happy to answer them, and I look forward to seeing many of you on the physics course next year. Thanks very much.